The ultimate endurance test. These pieces of yard equipment are being mercilessly tortured. This will reveal whether they're tough enough for everyday use. They have to survive drop tests, withstand intense UV radiation and extreme temperatures. They're mass-produced on state-of-the-art assembly lines. Engineering plastics are united with specially hardened metals on gigantic robotic assembly lines. Testers push materials and machines to their limits. Months of use are simulated in endurance tests.
We test the product till it fails.
And they pay particular attention to the safety features and the effect of all conceivable types of misuse. Operator safety is just as important as a long service life. Contrary to expectations, even yard equipment manufacturers continually optimize their testing methods and manufacturing processes, and all with the goal of making the perfect yard helper. Because in the end, only the toughest make it into the yard. In this machine shop near Ulm, they start making new pruning shears for the coming summer in the winter. The workers here produce 9,000 units a day. Most of the work is done by computer-controlled robots. All of the components must be manufactured to extremely tight tolerances, so that everything fits together perfectly at the end. Pruning shears like these consist of 15 individual parts. They are so-called bypass shears. The two blades pass by one another when cutting. This results in precise, clean cuts. Bypass shears are particularly suited to cutting plant shoots and flowers. These rolls of 3.7mm stainless steel are the starting material. From then, this machine punches out around 20,000 lower blades a day. The robot simultaneously stamps a groove into the steel, along which the sap can later flow. The delicate upper blade is cut out by this massive laser. It processes roughly 8 sheets an hour. The focused beam of light cuts through the steel like butter, producing a blank from the tough material in just 15 seconds, and does so with a tolerance of just a few hundredths of a millimeter. To ensure that the work runs smoothly and efficiently, the laser has a metal assistant. This robot, which is affectionately referred to in the factory as the Japanese one due to its country of origin, is a true multi-talent. It feeds the laser new material, removes the finished blades, and transports them to the first grinding station. In this machine, they are deburred, which removes any metal remnants, and then burnished. Afterwards, the Japanese robot carefully loads the blades into boxes, 100 units in each. The handles are often made from plastic. A suitable grip is required to transfer force to the cutting blades. This is provided by handles made from special plastic that's molded into shape in custom-developed machines. This is done in this factory near Stuttgart. The raw materials are polyamide and so-called ABS plastics. They're especially tough and hard, which makes them exceptionally resistant to wear and abrasion. For the handle to withstand the rigors of daily use depends on the right blend of various components. A worker fills the hopper of the machine that will make the handle with the plastic pellets according to a precise formula.
Using a high-tech plastic like this is really important for good handling. It goes without saying that the handle shouldn't break when I cut branches of different thicknesses.
The plastic pellets are now injected into the mold at 320 degrees Celsius and 1,700 bar. The robot keeps the pressure on until a permanent bond is formed. This ensures the plastic achieves the degree of hardness required for the toughest of gardening jobs. The process is known as injection molding. Around 1,000 different items for the gardening industry are manufactured in this way here. Each part is produced using a specially designed mold, the so-called tool. The workers refer to the room in which they're stored as the treasure room. The reason? Molds weighing up to 25 tons and worth upwards of 100,000 euros are stored here. Back to the blades in the machine shop near Ulm. At this station, the upper blades are transported by conveyor to an illuminated table. There, their positions are scanned so that a robot knows precisely how to pick them up. Now, the so-called surface and radius grinding process begins. The first robot immerses the blade in a tank with special abrading fluid so that it grinds the entire surface flat. A cooling lubricant prevents excessive heat being generated and the blade from breaking. Then it hands the blade to its colleague. It then grinds the convex edge, that is, the part of the blade that does the cutting. The robot clamps the blade in another grinding cell, after which it's deburred. The main and secondary cutting edges are now razor sharp. So sharp that these workers have to take extra care when handling them. The blades now set off on a wellness trip. The neatly arranged blades first visit the in-house cosmetics department. The wash booth has 5 different zones, where special detergents are used to remove residual oil and dirt, and an anti-corrosion coating is applied. The brightly polished parts then enter the paint booth, where a painting robot gives them a manicure. The blades are spray-coated with a special lacquer before heading to the first of 2 chill-out rooms to pre-dry. This is important to prevent the paint from blistering. The paint is then cured at around 200 degrees Celsius before the blades head to the second chill-out room to cool down again. This precise sequence of steps ensures that blade and coating are equipped to deal with the widest possible range of weather conditions and usage scenarios. Meanwhile, the bottom blade or hook is hardened in the oven. It's first heated to 1060 degrees Celsius before being immediately quenched in a second chamber, a bit like taking a sauna. The aim? To achieve a hardness of 52 HRC, similar to that of a Swiss Army knife blade.
This process is important because otherwise the blade would be too brittle and could break if dropped.
The blades and handles are united on the assembly line. These workers make around 2,800 pruning shears per shift. They assemble the larger parts of the shears themselves and place them in workpiece carriers. Then things become more detailed, and another machine takes over. It integrates the spring into the shears, where it's protected against dirt and from getting lost. Then it attaches a lever that allows the grip width to be adjusted to fit different hand sizes. The pruning shears are now nearing the end of their journey. The machine installs the safety lever, which locks the razor-sharp tool closed and tightens the last of the screws with a precisely defined torque. Man and machine check once again that all the parts are correctly assembled and that the shears function. Then they can leave the factory. In this lab, the developers test individual shears under extreme conditions. They have to withstand extreme stresses intended to simulate several years of yard use. The first test is intended to push the handle spring to its limits. it has to endure 70,000 cutting actions without fatiguing. Yard tools are sometimes misused. The test simulates cutting material that is too thick or too hard, such as metal. Here, 500 newtons are acting on the blade, which is attempting to cut through a steel pin instead of a branch, and it mustn't break in the process.
We're pressing down with a weight of 50 kilograms, which is like stepping on it and trying to cut through a steel pin. So it really is the worst case scenario.
In the best case, the shears do what's expected of them. In this test, they have to cut through a hard beechwood stick 5,000 times and still work properly afterwards. There are around 350 tests used to test the shears and other equipment down to the last screw. This engineer is testing the most important safety feature. Should the shears be dropped from a hand height onto a hard surface, the safety lever securing the blades must remain locked in order to prevent injury. To check this, the shears have to survive being dropped 18 times without the jaws springing open. If the branches get too thick for pruning shears, more powerful tools are required. In this enormous factory in Baden-Württemberg, they make chainsaws. The saw bodies are built at 13 workstations on one of the many assembly lines. How many chainsaws are manufactured each day is top secret, as is the number of individual components they're made of. The developers regularly push the saws to their limits in around 100 endurance tests. The saw has a 42.6 cubic centimeter 2.7 horsepower engine. It's primarily used for delimbing and cutting firewood. Manufacturing the saw body is a complex process, and all work steps are perfectly synchronized, like the cogs in a precision timepiece. Special care is required at the first station, because the piston is fitted with two delicate gaskets. If they were to get damaged when the piston is inserted into the cylinder, it could mean the saw not working at all later. The job of applying the sealant is precision work and done by a robot. Then it's the assembly technician's turn again. He fits the crankcase and then the parts are married. Once the engine is sitting properly in the casing, the worker places the newlyweds on a conveyor belt for further processing. Humans and machines work in close concert here. At the first of the automated stations, the main part of the saw is screwed together. Each screw is tightened with a specific torque. The assembly line computer logs every activity. After rounding the first corner, the saw body undergoes its first test. The cylinder is sealed tight and filled with compressed air to check for leaks. If there were any, the saw would probably still run, but be incapable of developing any power. The saw body is cleaned with a special fluid here too, then continues on its journey. This worker installs the oil pump and screws the clutch into place. Then he installs the spark plugs and flywheel. The workers are so experienced that they can tell if something isn't right just by the sound of the components. The muffler is made from especially thin sheet steel in order to keep the weight of the saw to a minimum. At the next station, the handguard and chain sprocket are fitted. If the handguard is triggered while sawing, the chain must come to a standstill within milliseconds. At the end, the worker attaches the fuel tank assembly, and then it's off to the next testing station. Here, optical sensors scan approximately 28 characteristics, which are then compared against an image database to check that they match. Finally, the workers install the starter assembly and air filter, and the saw is ready to be dressed. This worker checks one last time that nothing is missing and then fits the housing. The saw body is now complete. The guide bar and chain must be light, yet stable. The guide bar is 35 centimeters long and made from especially corrosion-resistant steel. A laser cuts it to shape. It consists of 3 sheets of metal electro-welded together. The chain will later sit on the middle one. The chain is supplied by a factory in Switzerland. Every tooth is individually sharpened. In this version, the chain has 44 teeth. The saw body must still undergo 2 final inspections, which will decide whether or not it will soon be allowed to leave the factory as a chainsaw. First, a worker tests the covers and levers and checks the computer to see if everything is fitted that should be. In this way, manufacturing defects can be traced back even years later. The moment has arrived. The saw is brought to life for the first time. In the testing booth, power output, exhaust emission values, brake and throttle trigger lockout are carefully analyzed, as well as idle, start and stop functions. The saw body gets the green light, but its journey is not over by a long shot. It will be pushed to its limits over the course of around 150 endurance tests, but more on that later. In the Austrian town of Langkampfen, the terrain for the domestic yard is patrolled. Green blood flows through the veins of the workers at this factory. They build robotic lawn mowers that can maintain lawns completely autonomously. The components come from all over the world. The robotic mowers are designed to do their job entirely on their own. To ensure mistakes don't occur, they undergo rigorous safety testing and quality controls. This assembly line is one of 23 at the factory. It's where robotic lawn mowers capable of maintaining up to 4,000 square meters of lawn are born. The mower is composed of around 100 components comprising electronics, mowing unit, chassis, and casing. The cover protects its vital organs against rain or too much sun. At the first station, workers install the blade. It will later spin at roughly 4,000 revolutions per minute and is subject to tight tolerances. Then comes the chassis, which also contains the electronic brain of the robotic mower. After that, the technicians fit the wheels to the drive axle. They're made from special plastic components and are especially robust. The red stop button being installed here is a safety feature that ensures the blade stops immediately in an emergency. Now, the technicians fit the cover. It's made from so-called ASA, a UV and scratch-resistant plastic that can withstand high temperatures as well. The cover is also important for the mower's structural stability.
We use a honeycomb design here. An idea we copied from bees. They're some smart animals. It makes the whole thing rigid.
The mower now heads to the first testing station. This machine tests the most important functions. This includes safety features like the sensors for detecting obstacles, switching functions, the blade motor, and the blades. The docking station isn't just for charging the mower's battery, but acts as a kind of theft protection as well. Without it, the mower won't work. The finished robotic mower is now boxed up together with its partner. Located behind the assembly line is the quality control department. Here, some of the new robotic mowers are immediately taken apart again, but just on a random basis. The workers check whether all the parts have been screwed together with the correct torque and whether the right blade, electronics modules, and motors have been installed. Any mistakes are detected here immediately, so the production line can be stopped and reconfigured in good time. This expert is testing whether all the functions work reliably in practice. Once the mini-computer has identified its docking station, it drives off. Safety features, braking times, and the sensors are closely scrutinized. In the yard, a perimeter wire helps the robotic mower to get its bearings. Having navigated along the wire once, it memorizes the layout and creates a mowing plan that ensures the lawn is always kept at the desired length. It cuts the grass clippings into tiny pieces and leaves them on the lawn as a natural fertilizer. But every now and then, it encounters obstacles. Sensors under its cover tell it which is the best direction to get around them. The developers have devised a special test to cover the situation where the sensor fails to detect an obstacle and the mower drives over it. The blades of the robotic mower rotate at around 4,400 revolutions per minute. If an accident caused a part to break off, it could become a dangerous projectile.
It could happen that the mower runs over a tree root, stone, or installation that's sticking up out of the ground, and the blade must under no circumstances break, or any bits get flung out that could injure someone. That's what we're testing here.
To make sure this won't happen, the developers place the robotic mower in a specific position. Start the blades up and fire a steel bolt right between its ribs. The mower is positioned in such a way that the bolt hits the blades in the most vulnerable spot and causes the maximum stress. In this way, the developers can be confident that in the event of a severe impact, the blades will absorb all of the energy and not transfer it to another component. The benefit of this is that the mower itself will still be fully operational afterwards, and only a bent blade has to be replaced. The robotic mower is told how and where it should mow, how it should deal with obstacles, and where it currently is by its printed circuit board. It's like the mower's brain. Without this circuit board, it would just be a battery-powered lawnmower. To keep the delicate circuit board safe, it's installed behind the robust suspension assembly. All of the robot's intelligence is on this board. It consists of roughly 1,200 components and provides all the motors, sensors, and displays with information.
Robotic mowers do their job in all conditions. It's like a mobile computer, I always say. As such, it's essential that the electronics are robustly designed and tested to ensure the mower works safely and reliably, whatever the conditions.
Behind this meter-thick door lies one of the most modern anechoic chambers in Europe. Its design is unique. It sits atop a 25-ton decoupled foundation. The orientation and position of the mower and the 6 microphones within the chamber must be absolutely precise. This is essential in order to accurately measure the sound emissions of the machine. In addition to making sure the mower operates as quietly as possible, the acoustic measurement is also used to assess the durability of its components. Based on the various noises, the engineers can tell whether there's an imbalance somewhere that could result in certain parts suffering damage over the long term.
It's really important that all rotating parts are fabricated symmetrically and are in balance. We have very high standards when it comes to the quality of the parts. If we didn't, it wouldn't just mean higher noise emissions, but greater wear too.
The outdoor testing ground. This is where the computer-controlled yard helper has to demonstrate what it's learned. All manner of obstacles and challenges are installed on the 1,000 square meter plot. The developers observe very closely how it copes with them. Bumpy terrain poses a particular challenge for the little robot. An incline of up to 40%, on the other hand, is no problem. But it must also be able to recognize when a slope is too difficult, switch off the blades, and turn around. If it gets tangled in branches, the so-called bumper sensor is triggered. The mower then heads in a different direction in an attempt to free itself. It also gives larger bushes and shrubs a wide berth in order to avoid getting caught in them. The developers use the findings from its run through the obstacle course to constantly tweak the mower's capabilities. Having completed all the tests, it heads unerringly back to its docking station to replenish its energy reserves. Energy for its next mission. Back in Germany, the chainsaw must now demonstrate what it's capable of. At this test station, the saw is mounted on a sawing robot. The engineers conduct an endurance test to discover where potential weaknesses are that could compromise the cutting performance of the guide bar and chain. Which is why the robot shows the saw no mercy. In 50 hours of continuous operation in the testing lab, it simulates 500 hours of forestry work. The challenge here: the logs vary in hardness and thickness. The robot has to continuously adapt to the situation. It does this by varying the engine speed. On average, it runs at 9,500 RPM. The stress on the chainsaw is enormous because the robot doesn't give itself or the saw a break.
It's subjected to a great deal of stress here. It's cutting continuously. As such, the saw has no time to cool down. So we reckon the stress here is 10 times what it would be in the real world.
The robot is merciless and doesn't allow the saw a second to catch its breath. This increases the stress on the materials exponentially and means potential premature damage will be revealed here on the test rig. It's important for the testers to exceed the real-life stress limits and cover as many usage scenarios as possible. It also allows the engineers to more easily identify where material fatigue could occur when the components are examined later. The engine is scheduled to undergo a marathon series of tests too. In this chamber, real-life field testing is simulated. That means 150 hours of continuous operation in this testing booth.
We're conducting a so-called highly dynamic endurance test here. The data for the program being used for the endurance test was recorded beforehand by a user in the field in order to replicate the exact speed ranges used in real-world applications.
A saw like this is primarily used for delimbing, felling trees, and cutting firewood. That's what the program simulates. During the test, the saw must not overheat, exceed the maximum speed range, or lose power. Starting now, the motor will run continuously for nearly a week, which is the equivalent of roughly half a year of forestry work in time-lapse. This allows the developers to check whether the saw will achieve its design service life in practice. The high speeds not only cause material fatigue. Something that isn't immediately obvious to most people is that the enormous vibrations that occur not only cause the entire saw to vibrate, but are also passed on to the person holding it. Over the course of an 8-hour working day, a forestry worker cuts for 3.5 hours on average. Excessive vibration can, in the long term, lead to serious circulation problems and numbness in the hands, so-called Raynaud's syndrome. For this reason, the developers in the sawing booth must, or rather are allowed to, operate the saws themselves.
We measure the accelerations at different locations on the saw, use them to determine transmission pathways to the handles, and familiarize ourselves with the machine so that we can develop ways to reduce vibrations for the operator. It's always a highlight. It's great being able to make cuts and test the saws yourself.
The saw is tested at idle, under acceleration and full load at maximum speed and in all imaginable cutting positions. While doing this, sensors attached to the handles measure the vibrations and transmit the data to a computer. Based on the results, the engineers can work out how the machine has to be constructed in order to minimize the transmission of vibrations to the operator. Most chainsaws have a so-called anti-vibration system. It's a combination of special springs and precisely calculated buffer zones that absorb the vibrations generated by the motor and saw chain. These special springs are the focus of work elsewhere in the development department. During the handle strength test, the developers test how sturdy the handles of the saw are. If the bar of the saw gets jammed, say when cutting through a tree trunk, the saw operator tries to pull it free, and the handle mustn't break off in the process. First, the developer checks how much force a person can actually apply when pulling. In this case, it's 309 newtons, or roughly 31 kilograms. The equivalent of 2 full crates of beer is now hanging on the saw. To be absolutely confident that nothing can happen, the stipulated test values are actually 4 times as high. And to be safe, the developers put an extra 10% on top of the iron weights. They load the handles of the chainsaw from different directions. The material withstands the test, and there are no noticeable changes, even at susceptible locations. Should a weakness be found, however, the developers immediately begin working to improve the handle.
First of all, we check if it's an overload failure. Is it a failure that could happen in everyday use? If this is the case, we review the calculations and check at what point the material failed, and then strengthen it there.
The engineers continually develop new tests in order to test even parts of the saw that wouldn't be affected by normal use. The most important safety feature of the saw is the chain brake. If the saw operator releases the throttle lever, the chain stops immediately. In emergency situations, it's possible that he isn't able to, which is why the saw is fitted with a hand guard that is also connected to the chain brake. If the saw operator strikes the hand guard, the chain stops in just a few milliseconds, like slamming on the brakes in a car. The force of the impact is often high, which is why the handguard must also be very robust. The developers check it with a specially developed impact test. They strike the handguard 20 times with a force of 10 joules, the equivalent of roughly 2 bottles of water. Should the saw operator stumble or even fall, he often reflexively drops the saw. If this happens, the fuel tank must under no circumstances break off and allow gas to leak and contaminate the forest floor. A drop test is performed, and the saw has to survive the impact unscathed. The saw is dropped from a height of 85 centimeters, which corresponds to the average height of a hand from the ground. The ground here is made from concrete, however. That really hurts. After that, the developers cool the saws down to -30 degrees Celsius in a special freezer. The material is now far more susceptible to damage. The engineers then repeat the tests in order to detect potential weak spots.
The saws get used in cold conditions too. Low temperatures represent the worst case for plastics, as they become as brittle as glass when cold.
External influences aren't the only things that can harm the saws. Danger can also lurk from within. Vibrations from the engine can affect all of the components. This test rig generates such large vibration stresses that it can simulate the entire lifetime of the machine parts. In this case, it's vibrating the muffler.
A device like this is capable of destroying itself if it's not designed and engineered properly. There are a lot of small parts inside that are also sensitive to vibrations, and we test them here too.
The muffler is especially susceptible. For weight reasons, the sheet metal it's made from is usually as thin as possible. At the maximum speed of 12,000 RPM, the parts are subject to a vibration frequency of 200 Hertz. Hertz stands for the number of oscillations per second. Because the operating life of the saw is being simulated in time-lapse, the parts are subjected to up to 800 Hertz. The noise generated is almost unbearable to the human ear. The test results help the developers to improve the manufacturing processes involved in constructing the chainsaw down to the last screw. Although it's still winter outside, yard equipment for the hot summer months is already being produced. In this 8,000 square meter building, they manufacture spray nozzles. Engineers can indulge their passion here. There's a lot of technology in a spray nozzle. A plastic widget in the grip serves as a frost compensator that can counteract the expansion pressure of residual water when it freezes. O-rings and inserts are installed in the head so that the spray nozzle remains watertight, even when subjected to 12 bar of water pressure, no matter which jet is selected. The grip is composed of two different components, a hard and a soft non-slip one. They're manufactured in a plastics processing facility in nearby Heuchlingen. Both components are fabricated here in a single molding step so that they are permanently connected with one another afterwards. At temperatures of up to 320 degrees Celsius, the pellets are melted to form a viscous liquid. The machine first presses the hard plastic into the mold. Once it has spread and begun to solidify, the mold rotates 180 degrees, closes again, and the soft compound is added. Manufacturing the spray head involves an additional challenge. It too is formed in a similar mold. And to ensure that it's absolutely watertight later on, the finished part must be symmetrical, in other words, round. Otherwise, the O-rings wouldn't fit properly. Because plastic can deform during cooling, the engineers have made the mold elliptical, that is, oval-shaped. As a result, the part becomes round by itself when it cools down. The most iconic aspect of the gardening industry is manufactured in this factory too. This connector is the link that joins the hose with the tap or spray nozzle. It's complicated to manufacture, as 3 parts have to be integrated in one step. The machine that makes the connectors is packed with advanced technology.
This machine is key. There's so much technology in it, hydraulics, pneumatics, and everything has to work in harmony. Although it only makes small parts, the mold weighs 7.5 tons and it operates 24/7.
The spray nozzle components now go by truck to Ulm, 100 kilometers away. In this factory, they're assembled to make the finished spray guns. At belt 1 of the assembly line, 15 automated stations assemble 23 individual parts to make the grip. The process depends on everything running smoothly.
The difficulty here is in operating the line with a 3-second cycle time. As soon as one cell comes to a halt, the entire production facility stops. When that happens, the downstream processes come to a halt too. So we have to make sure we produce the components here at the designated rate around the clock.
The robots assemble valves, seals, levers, and grips into the finished product in just 1 minute. With such a tightly synchronized production sequence, quality controls cannot be neglected. At the end of the assembly line, the grips are filled with different amounts of air and pressurized. If the curve on the display remains stable, there's no pressure difference. The grip is allowed to pass through, because it means the spray nozzle is guaranteed not to leak. At the next automated workstation, the grip and head are joined together. This is done using the so-called friction welding method. The materials are melted by rotating at 800 to 1000 RPM and securely joined together. So securely, in fact, that the spray gun can withstand a water pressure of 20 bar. At the next station, the sensors have detected a fault. When scanning the part, an infrared camera sounded the alarm. Now they have to take immediate action so that the assembly line gets up and running again without delay. A worker checks what the problem is. An O-ring has to be replaced. Then the process can restart. At the end, workers fit the spray head and the finished spray gun leaves the assembly line. Around 1.2 million units are manufactured here each year, and some of them are ordered by the quality assurance technicians to the testing booth. More specifically, the so-called washing pressure test booth. It's designed to really put the spray gun under pressure. It mustn't burst when subjected to the full force of the conduit water pressure. In most regions, this means it has to withstand a pressure of 2 to 4 bar. But that's not enough for the testers. They want to know exactly where the potential weak spots in the material might be, and thus test it to its limits and beyond. Some heads can withstand up to 40 bar. That's the pressure 400 meters underwater. An experimenter's delight. The standard values are naturally much lower. The next stress test looks comparatively harmless, but is vicious for the spray heads. Here, the closed spray heads are hit with a pressure of 12 bar, like the recoil of a pistol, many times in succession. 12,000 sudden pressurizations, one after the other. The small droplets of water come from the internal seals. They have to absorb the impacts and cause the spray head to literally sweat. Meanwhile, the spray guns in the next test are already soaking wet. In this endurance test, the developers are checking all 3 spray patterns with a pressure of 6 bar for 50 days. This corresponds to a year of normal yard use. The spray gun has to be able to cope with other extreme conditions too. It can heat up to 70 degrees Celsius when exposed to blazing sunshine. The engineers simulate this using an oversized sunbed in order to test the material properties. In the UV chamber, the skin of the spray guns is subjected to 1,700 watts of radiation for 5 minutes. This is the equivalent of 3 years exposure to the Australian sunshine in one go. This could cause the constituents of the plastic to disintegrate. Nonetheless, the skin of the spray gun mustn't become porous. In the seasons test, the devices switch back and forth between an ice bath at -10 degrees and a heat chamber at 60 degrees Celsius on a weekly basis. This allows the engineers to investigate the effects of seasonal changes on the materials and functionality of the yard helper. Once the tool has successfully completed all the tests, the gathered information is fed back to where its journey began. The engineers in the development department tweak further.
We take these requirements and think about what we can do with them. If a material is too soft, for example, we still have the option of using a glass fiber reinforced plastic or another soft component so that it feels much better to the touch. And with these factors and our experience, we continually refine the equipment.
Yard equipment is getting more robust and intelligent. From the first prototypes to the finished product, enormous robotic plants and high-tech assembly lines are necessary to combine craftsmanship with state-of-the-art technology. The equipment has to pass countless stress tests to show that it meets the high expectations of the design engineers. And the consumers? They have no idea about all that. They're just happy to have tools that make the yard work easier before enjoying a refreshing cold shower afterwards. At the end of all the testing, it's a bit like Darwin said, only the toughest survive to make it to the yard.